Okay, welcome to the second week of differential equations. In this week, we will be covering 1.5 through 1.8 as stated in the schedule. So the section is 1.5, linear first order differential equations. So I want you to quickly recall what we did last week. So obviously it was an introduction to what a differential equation is. We found solutions. We found general solutions. We found particular solutions given an initial condition. Uh, we definitely used a lot of integrating techniques. Specifically in 1.4, we worked with separable differential equations. And remember, if a differential equation is separable, you can, obviously separate x and y or isolate them on opposite sides of the equation and then use, again, integrating techniques. But the question is, what happens if a differential equation is not separable? So, obviously in 1.4, they were all separable, but what do you do when it's not separable? So, for example, let's just give you an example. So I'm going to say, let's just call this example 1. So I have dy dx minus y equals 11/8 e to the negative x over 3. So that's an x over 3. And then let's just write our initial conditions. So at 0, right, if x is 0, then my y-axis, or my y-intercept, is 1. Okay, so we're given our differential equation, our initial condition. So if I ask you to separate the variables, right, there's a few ways of doing this, depending how you want to manipulate it. So I'm going to go ahead and multiply both sides by dx. Because we can, so you can think of it as the LCM. So if you want, let's see, I'll just go ahead and maybe do this in blue. So I'm going to multiply both sides by dx. So when I multiply that out, I get dy minus y dx equals 11/8 e to the negative x over 3, or a third x, dx. Okay, so I've cleared, some of my fractions in terms of dx. And I want to isolate x, right, and y, obviously on opposite sides of the equation. So this guy looks nice, right? This is a function of x. This is 11/8. This is obviously just a constant. So function of x, dx. I have a function of y here, here's a function of y. I have my dy, but it would be nice if it was a product. My y is next to the dx, so I want my dx on this side. So what if I add this expression to the right-hand side? Well, if I do that, I get dy equals the following. So then I'm adding y dx. And then we're here, and okay, I have dy. You can think of this as 1 dy. Again, my function of x dx plus, and then I have, again, this function of y dx. And we can go, we can subtract this and but we're just going to go backwards. So this differential equation is, so dot, 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 if you keep trying. This differential equation is not separable. Right, so not all differential equations are separable. When they are, I would attack it by separating the variables. But in this case, again, we can't separate the variables. So what do? Well, there's another technique, obviously in 1.5, which is linear first order differential equations. So we need to discuss, we need to talk about what linearity is in order to talk about this method. So notice again, we have linear first order differential equations. So we know what first order is, right? The highest derivative is 1. We obviously know what a differential equation is. Now we need to talk about linearity. So what do I mean by a linear differential equation? Well, I'm just going to really go back to algebra, because if you understand what a linear algebraic equation is, a linear differential equation is, it's analogous. Obviously, we have derivatives with differential equations. So just quickly, so recall, right, maybe from your any algebra class. So a linear, let's keep this in green. A linear, actually, let me. Oh, I'll just keep it. Okay, so a linear algebraic equation, and we have a linear differential equation. Okay, so I maybe make this a little bit smaller. Okay, so what is a linear algebraic equation? Okay, a linear algebraic equation is of the following form. We have I don't know, y1 plus b, y2 equals c. If you want, you can even write ax, plus by equals c. And remember that, right, x and y, or y1 and y2 in this case, would be your variables, and a, b, and c would be arbitrary constants, right? This is basically the equation of a line, hence the name linear, right? That means we have a line, right, with a specific slope, or maybe undefined slope. So that's what a linear algebraic equation is. So a linear differential equation is, and let's see if I can fit this in. Okay, so that's, I would just maybe box that. I wanted to do it here, but I think I'm just gonna, I don't want to restrict my thinking here. Okay, so a linear differential equation is the following form. It is a of x, y prime plus b of x, y equals c of x. Now I want you to notice the similarity. So I'm using this guy again. X and y, y1, y2 are just variables. So the form looks very similar. A times a1, a of x, okay, my y1. The reason I chose y1 and y2 is to help you think of the derivatives here. I mean, that's the first derivative, okay, and then no derivative. That's our solution. But again, b of x, you have c and you have c of x. But here, a of x, b of x, and c of x are not necessarily constants. They could be constants. I mean, a constant is a function. Again, a nice horizontal line, but not all functions that we work with are horizontal. So the main thing here is, so a of x, b of x, and c of x. So let's maybe point at these. These guys are specifically, these are known, right? We know these functions. Known functions of x. Okay, that's important, of x, not of y, because y is, again, our independent variable. So this is a first, this equation is linear, and it's actually a linear first order differential equation, as the title stated, because the highest power is the first derivative. So again, let's go ahead and write that down. This is a linear first order differential equation, so linear. And we're going to be talking about higher order differential equations, not in this section quite yet, but let's just go ahead and write the second order because it's actually not that hard. So if this is the first order, well, a second order definitely has, the highest derivative is 2. So let's just say, a of x, okay, y double prime, plus b of x, y prime, plus c of x, y equals, d of x. And I chose a, b, c, d. It could be e, f, g, h if you want. I'm just choosing a, b, c, d. But again, these functions, right, this is a known function of x, known function of x, known function of x, and known function of x. Where, again, it's linear. It has this nice form. such as, I mean, this guy. But again, second order, we can do it with a triple derivative and so forth, but we're going to be working with the linear first order differential equation. And let's see, I'm at 10 minutes, so I'm going to stop here and then quickly give you some examples of with concrete. I mean, these are very general or abstract. So I want to give you concrete examples of linear differential equations and also nonlinear differential equations, and then start some examples.